Start. So, good morning and good evening, everyone, wherever you are. Thank you for joining us. I'm Mary Salvana, Assistant Professor in the Department of Statistics at the University of Connecticut in the United States. On behalf of the organizing team, I am pleased to welcome you to the High Performance Statistical Computing, or HPSC, presentation series. Each seminar runs for 60 minutes. The speaker will present for 45 minutes, followed by 15 minutes for questions. Please feel free to type your questions into the chat at any time. We will collect them and raise them during the Q&A. All talks are recorded, and the recordings, along with the slides, will be posted on our website. We typically host one seminar each month, and you're also welcome to nominate future speakers. To stay updated on upcoming events, you can subscribe to our mailing list, and you'll find those details as well as other resources at hpscforscience.org. Before we begin, I'd like to briefly mention that we also have an invited session at the Joint Statistical Meetings this year, or JSM 2026. The session is called High Performance Statistical Computing: Challenges, Opportunities, and Future Directions. The session will take place on Thursday, August 6, 2026, from 8:30 to 10:20 a.m. in Boston, Massachusetts. We would be delighted if you could join us for that session as well. With that, I'll introduce our speaker for today. Lisa Gaedke-Merzhäuser is a postdoctoral fellow in statistics at KAUST, Saudi Arabia. She holds a PhD in computational science from Università della Svizzera Italiana, USI, in Lugano, Switzerland, and a master's degree in mathematics from Freie Universität Berlin. Her research interests lie in fusing statistical learning techniques with methods from high-performance computing with a focus on scalable spatio-temporal Bayesian modeling. We're very pleased to have Lisa with us today. Lisa, thank you for joining us, and the floor is yours.
Thank you. Hello, everyone. And thank you very much for the invitation to give a talk here today. So yes, as Marianne was mentioning, I'm a postdoc at KAUST in the Bayesian Computational Statistics and Modeling group that is led by Robert Roux. And my main research interest actually aligns very well with the name of this seminar series and this community, as the main aim of my work is to bring some more HPC into Bayesian statistics. And today I would like to talk to you about a project that was done in collaboration with ETH Zurich and USI, where I did my PhD. And here we developed a Bayesian inference framework based on the methodology of integrated nested Laplace approximations for spatio-temporal multivariate Gaussian process modeling. And this was published at SC25. This is a big supercomputing conference. And the talk that I will give today will contain some parts of our talk at SC, but because I have a bit more time today and because the audience is maybe a bit different, I also took the liberty to add some more details from the methodological side that didn't fit so much the scope of supercomputing. And in case you've attended last month's talk, this is actually a great continuation of what Yin has been presenting, because she already exposed us to many of the concepts that will be relevant today. And there will also be some similarities in the applications. So let's start with a little bit of a motivation. So suppose that we have some data that is collected over space and time, and we want to better model and understand the behavior of the underlying process. And more concretely, we looked at air pollution over Italy and considered particulate matter concentrations with a maximum diameter of 2.5 micrometers, with 10 micrometers and ozone. And what we wanted to do is to jointly, there's the animation on the right. And here we can see 3 different measurements for all those quantities at selected locations over time. And what we wanted to do is model those air pollutants jointly to better understand their correlation, refine the spatial resolution of the data that we had available, and be able to account for uncertainty as the data is mostly satellite derived and therefore can be prone to inaccuracy. Now, how did we do that? We used spatio-temporal multivariate Gaussian processes, as they offer a very flexible framework to capture these kind of complex behaviors, and used a Bayesian approach in order to include some prior knowledge in our framework. However, the main challenge that also Yin has been discussing last week for these high-dimensional Gaussian processes, and then especially in a Bayesian context, is the high computational cost. And there are, I would say, two ways that you can try to lower this cost. And one is to find a methodological formulation that will provide accurate results, but at a lower computational cost, and to develop efficient implementations that make use of all of the relevant tools that we have available in our high-performance computing toolbox to get to a solution faster. We try to utilize both, and I will start a little bit from the methodological side and explain a bit how we constructed our model. So before going into space-time, let's start with the spatial model. And the de facto standard in spatial statistics is to use a Matern covariance function, which you can then use to construct a covariance matrix where you compute the pairwise distances between two spatial locations, and this will tell you something about their correlation. And we have that where points are closer together, you expect a higher correlation than when points are far apart. And so this will describe the dependence between the different variables in those different locations. And then you can equivalently consider this linear fractional SPDE. And Peter Whittle showed already in the late 50s or early 60s that the solution to this linear fractional SPDE that you see here, so the solution U, has a Matern covariance function. And here delta is the Laplace operator, and W represents Gaussian white noise. And then this differential operator that you have can be used to construct a precision matrix. So the precision matrix is the inverse of the covariance matrix. So from a mathematical perspective, it contains exactly the same type of information as you can go from one to the other. However, from a statistical perspective, they differ in the sense that the precision matrix describes the conditional dependence between variables, and it has this property that whenever an entry between two variables is 0, it means that they're conditionally independent. Now, let's get a bit more concrete in how we can use this to construct a precision matrix. So you can discretize this SPDE using first-order finite elements. And Lindgren and co-authors showed that this finite element approximation of U of S forms a Gaussian Markov random field, which in the limit will converge to the true underlying solution of U of S. So the picture on the right that you can see, so the first one, the one more from the left, shows the true underlying Gaussian field, and on the right you see the Gaussian Markov random field approximation. And so because finite elements are so extensively studied and have been for a long time, there's a lot that we can take from this, for example, in how to construct suitable meshes that will give us solid properties. And most importantly, because we construct our precision matrix from a finite element discretization, the resulting precision matrix will be sparse. So this means that the precision matrix is sparse, while at the same time it's inverse, so the covariance matrix is dense. And on the right here, we can see two examples for sparsity patterns of precision matrices coming from spatial fields. So the first one is not in any particular order. And the one on the right comes from a sphere, so from a discretization on a sphere, which is another very nice property that comes from this SPDE, that we can easily discretize it on manifolds. So it could be a sphere, but it could also be a much more complicated shape. Additionally, we have that the mesh that we construct is independent or can be independent from the observation locations. And this makes the formulation of our model independent of where the data is observed. So we could use the same model for two different types. So for different, obviously on the same domain, but different batches of data that were observed. And it also means that our model will scale with the number of mesh nodes and not with the number of observations. And then one can show that in the limit, both approaches will converge to the same solution. Now I've been talking about a spatial approach. However, we wanted space-time. So what we're actually using is an SPDE-derived spatial-temporal extension that now also includes a derivative in the first-order derivative in time. And here we can see a rising spacity pattern of the precision matrix on a sphere over 5 time steps. And I'll discuss this spacity pattern in more detail later on. Now, this was a bit the spatial or spatial temporal model component of our latent parameters. And now we want to look at a bit more details of the overall formulation. So we suppose that we have some data y that depends on our latent parameters x and some hyperparameters theta, together with some noise, and that they follow some likelihood that is parameterized by those unknown parameters. And then we have the latent parameters that we're interested in, which follow this Gaussian Markov random field. And this contains the spatial or spatial-temporal component, but it can also contain other random variables, such as an intercept or elevation information. So anything else that you would like to add to your model. And here we assume this Gaussian prior on our latent parameters, and finally some hyperparameters that parameterize the precision matrix Q, and that contains other sort of more global attributes like the spatial range or the temporal range of our process. Okay, and because this wasn't enough, we now want to combine multiple of those models, as we want to jointly model multiple observed quantities, right? We had these different pollutants. And so here we follow an approach that is called linear models of co-regionalization, which is quite commonly used in this context. And the main idea is to model each process as we discussed before, and then connect them using this lambda matrix. So here, lambda contains these coupling terms that are denoted by lambda 1, 2, and 3, and scale parameters sigma I for each field. And then we have this for each pollutant. So let's say we order it by PM2.5 first. So then this would correspond to lambda 1, and then maybe PM10 would be lambda 2. And then the resulting precision matrix that we obtain has the following form. So we have the univariate spatial-temporal precision matrices in here, and then we have the inverse and the transpose for lambda. But because of this structure of lambda, the inverse will remain sparse. So we will get the same sparsity pattern, and therefore our overall Q remains sparse as well. Now, how do we get to the inference part? How do we do inference? So before I get into more technical details, I want to argue that the Bayesian way of thinking is actually how we kind of think every day. So if I show you this image and I say, wow, can you complete it in your head? You've probably already done that. And why can you do that? Because you have some prior knowledge. You've seen a flower before, and you have a general understanding of what you probably see. And so then you can just combine it to a complete image. And this is a little bit what Bayesian inference formalizes. So the main idea is to update our beliefs upon observing data using Bayes' rule. And if we want to express this mathematically, we can do this by putting a prior distribution on our parameters and a likelihood that describes the distribution of our data, which we then combine using Bayes' rule to a posterior. So here's Bayes' rule. And while we have all the quantities available on the right, we typically don't have a closed form of this posterior on the left, which is actually what we're interested in. And therefore, we don't really have an overall understanding of the shape of this function. Now, in our case, it's actually even a bit more complicated because we have these two stages of parameters. So now here highlighted in red, we also have this dependency on x, but the general principle remains the same. And we have the same problem that there's no closed form of the posterior. So this is why Bayesian inference algorithms or methods have been developed. So generally, they can be split into two types, into sampling-based algorithms, where we mainly have variations of Markov chain Monte Carlo methods, and they're typically considered the gold standard as they're asymptotically exact. However, their parallelization potential is quite low, but they're very broadly applicable to pretty much all types of models. And then we have deterministic approaches, most commonly used variational inference, which is much less accurate, but bears a much higher potential for parallelization and is also broadly applicable. And then we have integrated nested Laplace approximations, or short INLA, which is also quite accurate. It has a high parallelization potential, but is more restricted in its applicable model class, namely to latent Gaussian models. However, as we've seen in our formulation before, we actually have a latent Gaussian model, and so we can apply it in this case. And so this is what we'll look at in a bit more detail now. So how does INLA roughly work? The main idea is to construct a pointwise approximation to our posterior of interest, where we actually consider its negative log. And in the first phase, INLA performs an optimization over the hyperparameters theta to determine the optimum of our objective function f, which corresponds to the mode of the posterior of interest. And here, the mode is found using a BFGS algorithm, which requires the value, which requires us to compute f at the current iterate and its gradient at that current iterate. So we have all these repeated evaluations. And then to dive a bit into the underlying linear algebra, the main computational bottleneck operations that arises in evaluating f is the evaluation of two high-dimensional multivariate normal distributions. And I've written because we consider the log, we have the log normal. And so here I've written out the formula. And to evaluate this for a specific value of x and theta, we need to be computing the log determinant of our precision matrix Q that will change every time theta changes. And Q is, as described before, sparse. And here we then compute a sparse Cholesky factorization of our precision matrix. And then from this Cholesky factor, we can easily compute the determinant. And subsequently, we also perform a triangular solve in order to compute this conditional mean mu of theta that you see here. So that also has a theta dependency. And now in the second phase, we are approximating the marginal distributions from which we can then also derive other statistical quantities of interest. So from a computational perspective, this requires us to perform further functional evaluations of f around the mode of theta that we've previously determined. And then additionally, we need to compute selected entries of the inverse of Q, so selected entries of the covariance matrix. Now, if you have a sparse matrix and you generally require entries from the full inverse that span across all columns, you need to just compute the dense inverse, right? And this will typically be dense. And then you can kind of select those entries that you're really interested in. However, this is very computationally expensive and also requires a lot of memory just to store all those entries. And therefore, so-called selected inversion algorithms have been derived to circumvent this problem of having to compute the full inverse, which instead operates on the sparse Cholesky factor of the original matrix, which leads to tremendous speed up and memory reduction. Okay, time to look at some software. So the reference implementation of inlies through the R-inler package. It's widely used in the statistics community, written in C with an R interface. It operates on shared memory parallelism by supporting a nested OpenMP scheme and relies on the sparse direct solver Paradiso. It comes with some limitations, namely that it doesn't support distributed memory parallelism or GPU acceleration, and it is not very modular, which makes it a bit hard to address the previous two limitations. So it's a bit hard to add to. And this is what has motivated our work on a framework called Dahlia. And here we really tried to address those before mentioned limitations, first by taking a modular approach where we really try to separate the statistical model from the methodology and sort of the back-end solver operations that can also be tailored to the problem at hand. So using a dense solver when this is the most convenient, using a sparse solver when this is the most appropriate choice, or a solver for a structured sparsity pattern. In terms of implementation, everything is implemented in Python, and we're performing array operations using NumPy and CuPy. So this directly enables us to use GPU acceleration. We have included distributed memory computing through MPI and Nickel, and then the sparse operations. So it's sort of the simpler operations, like let's say a sparse matrix-matrix multiplication is handled by SciPy. And then for the computational bottleneck operations, we are relying on a solver called Serinf to do that operates on structured sparsity patterns. And before we dive into the solver, I want to talk a bit more about the sparsity patterns that arise. So we looked at these univariate spatio-temporal models. And here we can see yet another sparsity pattern. And you can see here now that we have this block diagonal sparsity pattern. Block tridiagonal, where here first I'm highlighting the diagonal blocks, then the off-diagonal blocks, making it block tridiagonal. And then we also have this arrowhead structure, which we didn't see before in the spatio-temporal field. And those ones arise by conditioning on data. So then we get some fill-in in this arrowhead structure. And then for a trivariate spatio-temporal model, we obtain the following sparsity pattern. So this comes from this multiplication with this lambda matrix that I showed before. And we see here now that sort of each of the individual components maintain this block tridiagonal structure. However, overall it is lost. And this comes from the fact that we have ordered the matrix first by variate, so by pollutant. What pollutant are we considering first? And then each pollutant over time. So these are the different pollutants over time. And then we perform a permutation where now we order the pollutants first, our precision matrix first by time step and then by pollutant. So here now we have each time step, and then within each time step, the 3 pollutants. And so now we've recovered this block tridiagonal or sparsity pattern, so this structured pattern, where we can apply a structured sparse solver, which operates on dense tiles on the non-zero blocks. So each of the non-zero blocks gets densified, and then we use level 3 BLAS operations to perform Cholesky factorization, matrix multiplication, and triangular solve, operating on each of the relevant blocks. And the basic idea is that there's a forward decomposition, so the Cholesky factorization, and then a backward selected inversion for when this is needed in the second phase. And here's a little animation with the axis pattern. So this is for the forward pass, and then for the backward pass. So we can see that there is sort of this transition, yes, from the top left to the bottom right, and then back up. And in the work highlighted below, you can see how we've implemented this to do in a distributed memory fashion. So by distributing parts of these 2 different processes. But now let's return back from the solver level to the overall methodology. So when comparing these different Bayesian inference strategies, I said that INLA allows for more parallelism than some of the other approaches. And this doesn't just come from employing a distributed memory solver, but also through other parallelization strategies that I want to introduce in a bit more detail now. So we saw this optimization problem that we're solving, where we're using a BFGS algorithm. And here in every iteration, we require f as well as its gradient. However, we don't actually have the gradient analytically available. And so we're using a finite difference stencil or the finite difference scheme to approximate it. And this means that for each directional derivative, we're using a central difference, and we're computing sort of a little perturbation in both axis directions. And so we have these function evaluations of f around each local, like around each iterate. And those are actually embarrassingly parallel. So once we've computed where we need to compute f, we can perform those function evaluations in parallel. And then within each function evaluation, we can employ some further parallelism, where we perform those 2 high-dimensional precision matrix factorizations that I was mentioning before. So in our case, this can actually be done in parallel, which is due to the fact that here we are considering Gaussian data. And so we can split this in 2 branches and construct the matrices and then perform these 2 precision matrix factorizations in parallel. And what we can see here already is actually that there's a sort of a small load imbalance, because in one we're just performing a factorization, and in the other one we need to also do this subsequent solve that I've mentioned before that depends on theta, whereas in the other case this is for the prior, and so here we assume a mean of 0 and therefore there is no solve needed. But still, very much most of the workload can be parallelized. And now nested again within each function, within each factorization, we have the distributed structured solver that I was mentioning before. So this gives us 3 layers of sort of nested parallelism. Let's get to our experimental setup. So what we compared is our INLA with the sparse direct solver Paradiso as backend, to Dahlia with Sirin Fezit solver, where this is parallelized using OpenMP. And we ran RNLab with Paradiso on the Fritz supercomputer at FAU in Germany, which has very recent Intel CPUs. And then we ran Dahlia as it has GPU acceleration and distributed memory support on ALPS at the Swiss National Supercomputing Center on Grace Hopper superchips. And here we looked at a number of different benchmarks, and what I want to focus on today is weak scaling in time. So we considered a data set that consists of a spatial field with around 1,200 mesh nodes per output variable and ranges between 2 to 512 time steps, which ultimately leads to matrix dimensions between around 7,500 and 1.9 million, with the memory storage required for a single Cholesky factor going up to 115 gigabyte. And so what does weak scaling mean? It means that one scales the problem size with the number of processes in such a way that the work that is performed by every process remains the same. So ideally, we would like to the compute time to remain constant as we as we scale our problem to be bigger and add more compute resources. And so here we scale our problem in the time dimension. So we increase the number of time steps while keeping the other dimensions the same. And so here you can see our weak scaling plot. So on the x-axis, we show the number of time steps and respectively below the number of GPUs. So ideally, we would like to have a linear scaling in time. So we linear increase the number of GPUs with the number of time steps. And then on the y-axis, we can see the runtime in seconds. And then for RNLA, there's no distributed memory parallelism, so we can't increase anything. And so we just always run it in its most favorable configuration. And then the parallelism in Dahlia, we first do through the parallel function evaluations, then through the parallel factorizations, and then we parallelize each individual factorization using the parallel solver. And we can see here that with the smallest problem, we actually only get a speed up of a factor of 1.5, which mainly comes from the fact that this matrix is just very small. I mean, it's got 2 time steps. And also observe that this actually leads to superlinear scaling when going to one problem size larger, because the parameters that we're scaling are just not very representative of what makes up the runtime. And then from 16 GPUs onwards, we kind of see this expected scaling where we kind of slowly increase over time. And then here we timed out RNLA once it was 2 orders of magnitude slower than Dahlia, taking around 450 seconds per iteration. So because the number of iterations in our optimization problem are not always exactly the same, we just sort of did an average over sort of a fixed number of iteration to get a comparable timing. And then for the largest problem, Dahlia took 3.6 seconds per iteration, which means that it ran more than 2 orders of magnitude faster on a model that was 8 times bigger. We also looked at some strong scaling. So the idea behind strong scaling is to keep the problem size fixed while, and this is the problem size given on the right here, while one keeps adding compute resources. So ideally, when you double your compute resources, you would like your program to take half the time. And so here on the x-axis, we show the number of GPUs. while on the y-axis, we show, again, the runtime in iterations per second. And then in our inlet, there's only one configuration, so it's a straight line. And now here we can see that one iteration in our inlet takes around 44 minutes, and with Dahlia around 4 minutes, just using a single GPU. And then when we go up to almost 500 GPUs, it's more than 3 orders of magnitude faster. And then below, we have a graph with a parallel efficiency. So a parallel efficiency of 100% means that when you double the resources, you halve the runtime. And then a parallel efficiency of 50% means that by providing 4 times as many resources, you halve the runtime. And for the first part, where we can parallelize through these embarrassingly parallel function evaluations, we see that our parallel efficiency is pretty much 100%, like we would like it to be. And then when we parallelize through the second layer of parallelism, we see that it drops a little bit. And this is mainly due to this load imbalance that I was describing before. And then once we go into the parallelization in the solver, we can see that the parallel efficiency degrades, and this is due to how we were able to parallelize the factorization. Now, let's get back to our actual case study that we were initially interested in. So just as a little reminder, we wanted to jointly model these 3 air pollutants. And in the end, for this, we used a spatial mesh of around 4,000 mesh nodes over the course of 48 days, and included elevation and an intercept as covariates in our model, and wanted to then perform spatial downscaling, meaning that we wanted to increase the spatial resolution of our model by a factor of 25. And here we can see the spatially downscaled results averaged over all time steps. Blue indicates low concentration, and red indicates high concentration levels. And these time average results is actually what our collaborators were previously working with, as it was too computationally costly to introduce a time component. And then what we can see below now are the spatially downscaled estimates over time from Dahlia. And here we can see, especially for ozone, that in the central area, we have some days where the average really differs from what we get on particular days, which is something that would have been missed previously when you only work with these sort of temporally averaged data. And this already, brings me to my conclusion. I wanted to talk to you about Dahlia, our novel Bayesian framework for multivariate spatio-temporal Gaussian processes, which allowed us to scale beyond what was previously possible, as we saw in this high-resolution Bayesian air pollution study. In general, we are very much interested in further continuing our work on Dahlia and extending its capabilities beyond just multivariate space-time modeling. So in case you think you have an application that runs too slow and might fit our framework, please feel free to reach out to us. Or if you would like to contribute more from a performance side, we would also be happy to have a chat. And otherwise, I just want to point to our GitHub and say a quick thank to our sponsors, and thank you very much for your attention. And I'm happy to take questions if there are any.
Thank you so much, Lisa. That's a wonderful presentation. We have time for questions. If you have a question, please feel free to unmute yourself or type it in the chat. I'll read some questions in the chat if there are any. I have a question. Is Dahlia an R package? Is it in CRAN or It's just
It's a
Git.
Python package.
Okay.
Yes, I don't know if this is immediately off your list then. It's not on PyPy yet. It's mainly on GitHub. And if you're interested, we are very happy to support you in installing it. But there's also a very good README that my collaborator worked many hours on. So maybe you can even install it yourself.
So all the models in INLA is also in Dahlia or not?
So not all of them yet.
Mm.
We're kind of trying to currently focus on those that INLA doesn't handle very well, because we feel like those that INLA handles very well, we don't need to focus on so much. So we're more interested right now in kind of the edge cases. But there are some models that obviously double, right? Because there are some base cases that we just want to support for sure.
I see.
Do you have something particular that you're interested in? Maybe I can already tell you if we have that or not.
I'm just curious why, so is the plan to integrate this with INLA or they're going to be a separate?
So the plan is to kind of keep this a bit, like the plan is to keep this separate, but obviously to take the things that have been learned through constructing INLA, and to really, address a bit the limitations that INLA has. So there are so many things that INLA does very, very well, but then, some sort of like very high dimensional models, or we have some other models that have a bit complicated dependencies in the hyperparameters. And this is a bit complicated. Like I was saying, some models are a bit complicated to add in INLA. Like theoretically you could, but the way that it's implemented, you can't right now without a lot of work. And so, our plan is a bit to support those.
I see. Do we have other questions?
Hello, Lisa.
Hello.
Thank you. Yeah, hello. Thank you for this interesting talk. I have one question. It's more for statistics. We have multiple variables to model at the same time, right? Like the PM 2.5, PM 3, and ozone. And the sparsity pattern is the same for all of them, or is
Sorry, I think my slide sharing just stopped, no?
Oh, sorry.
Did it stop for you guys?
Yeah.
Let me just try again. Perfect. Okay, sorry to interrupt you. I'm back.
Okay.
So the sparsity, you were saying the sparsity pattern?
Yeah, is the same or not?
So for each of the different pollutants?
Yeah.
Yes. So, I mean, thanks for the question. So let me get back to where we can see the sparsity pattern. I think it's in the permutation, sorry.
No.
So it's actually exactly the same, and it comes from the fact that we don't base sort of our model on sorry, I got it now. So here we can see the sparsity pattern now. So yes, and it becomes from the fact that we don't tie our model to sort of where the observations are, because you could have a case, right, where for PM 2.5 you measure in this place, and for PM 10 you measure in another place, and then they obviously wouldn't be the same. But because our model is discretized using finite elements, our sparsity pattern comes from this finite element discretization. So the mesh is independent from where we actually have observations. And this is why we can have the same mesh. But theoretically, if you wanted to, you could choose a different mesh for each of them. I don't know if that would make sense. Maybe in an application where you have something that's very coarse and something that's very fine. But this would be a bit complicated to then project one to the other, but this theoretically you could do that. But so it's exactly the same, because we define the same mesh, the same underlying space-time mesh for all of them.
Okay, thank you.
There is one question in the chat from Anli. Can a spatio-temporal Gaussian process model handle a cold start scenario in which historical correlations are weak or absent, but occasional sudden spikes occur, as in my power network data.
Well,
Did
that's a
you-
very specific question.
It's a modeling question.
Yes. Marianne, can you maybe help me what the question means?
I'm not sure. Anne, can you turn on your mic or explain more? I'm not sure. Yeah. What do you think? Maybe you can give.
Can you read the question to me again, please?
Can a
Hello,
spatio-temporal go? Oh, yeah, somebody.
can you hear me? Can you hear
Yes.
me?
Yes.
Yeah. Now I have the power grid data. So they have a lot of substation. They have I think they have the correlation temporal and spatial. But so, as you know, some substation they have a lot of failures. Some substation they there is not a lot of failure or outage. So it means the cold start scenario. So in some days, for example, so there is some substation they are stable in many years, but some days they have a spike, they drop. So all substation belong to the networks. They have a correlation in the spatial and temporal. But so in the past, there is correlation is not good. Correlation about the failure. So how about we can apply the Bayesian spatial temporal Gaussian process for that scenario?
Thanks for your question. Okay, let me try. I feel like there's two possible ways I can see you might mean the question. So one way would be that you kind of have like missing data. Is this what you mean? Or the
I think that
or the other way
I think
is that you are asking if sort of in general Gaussian processes are well suited for your type of problem. Is
yeah
am I close?
yeah okay.
Is it the second type of question, or have I
No
not understood properly?
no yeah okay.
Okay, sorry.
Yeah. My question is very specific. Yeah.
Yes.
Well, now I am handling with the data. I think our data has the spatial and temporal. So maybe I think I can apply some insight from also research. Yeah.
So generally, I think when you have a Gaussian process, like the assumption, I mean, a Gaussian process has a smoothing property, right? So I think when you have things with very harsh spikes, maybe
Yeah.
like using just a Gaussian process is not enough. But I am unfortunately not the expert to tell you what you should do instead. But I'm sure in the audience there is an expert.
Okay, thank you.
Yeah, maybe somebody in the audience can answer that. We still have some time. There is another question in the chat from Lonnie Philip Tab. Will there be trainings for this in the future, similar to how INLA had or has trainings?
So I mean, we're in the beginning. I mean, ideally, we would like to support something like that. But if you would be interested in working with Dalia, just contact me directly. Like we're not at the scale of INLA by any means. So I mean, I will just contact me and tell me about what you would be interested in running, and we will help you to hopefully support that.
Any other questions?
May I ask?
Sure.
I work with using INLA. Is there pattern implementation for INLA, or how to integrate that of R with Python?
So you would like to run INLA in Python?
So what I know is INLA is existing in in R, right?
Yes.
Yeah. So is there a corresponding Python code for that?
So this is not part of the talk at all, but we have someone in our group who's actually making a Python package available called PyInla that will be a Python which has a Python interface, and it will call inla in the back, right? Because inla is written in C. Like there's no necessity to necessarily go through R. And so what he has done is to write a Python, just a Python interface to sort of the inla backend. So you should be able to run inla from Python with that. It's kind of in the last stages of, it must be coming out very soon. I don't know if you Google it right now, if you will find something, but I'm sure if you email me, I can directly put you in touch with them if you want to do something tomorrow. And otherwise, like it will come out in a month or two or something like that.
Okay.
Do we have other questions? So if there are no more questions, I think that's about it for today. If you have additional questions for Lisa, please feel free to reach out to her. Can you show your email address? Do you have it there? Or you
Well,
can Google her. She's quite famous.
I feel like my name is so particular. There's only one.
There's only one Lisa Gaedke-Merzhäuser. So yeah, we'll be posting announcements for our next seminar soon. Yes, we have once a month. So please keep an eye on your inbox in our website for updates. So thanks, Lisa, and thank you all for joining us. Bye-bye.
Thank you. Bye-bye.
Thank you.